So what we're going to do is we're going to drop a ball near the Earth and see what happens. So, extremely simple situation. We have a ball. Its mass is 100 grams, tenth of a kilogram. We hold it near the Earth and drop it. It travels downward 2 meters, speeding up as it goes. And the question is, what's the work done on the ball by the surroundings as it travels these 2 meters? So we get to review work here. So now be careful. I mean, this is an easy question, but you have to pay attention to signs, right? Remember, we noticed that last time. So, okay, so most people say the work is positive, which is correct. And let's remember why it is. We have the gravitational force pointing in the minus y direction. We have a displacement in the negative y direction. So what we've got, so if we started at 5 meters, the ball would have gone down to 3 meters. So we have Fy delta y is a minus 0.1 kilograms times 9.8 newtons per kilogram times negative 2 meters, isn't it? So we get a positive work. So the Earth does plus 1.96 joules of work on the ball. And so the ball is the system, the Earth is the surroundings. The work done is plus 1.96 joules. And what happens to the kinetic energy of the ball? It increases by 1.96 joules, doesn't it? So 1.96 joules of work done, increase in the energy of the system, 1.96 joules. Okay, simple, right? Now, we could also consider the system not just the ball, but the ball plus the Earth as the system. So now, it's legal to take two objects as our system, just as we ended up doing in the neutron decay thing, where we had a whole bunch of objects in the system in the second part. So now we're just going to go through exactly the same thing again, being very careful about to think about the definition of system carefully. So the work done by the surroundings means work done by objects that aren't in the system, right? And if the system includes the ball and the Earth, for that system, what's the work done by the surroundings? Okay, very good. That's right. The work done by the surroundings in this case is 0. Because there isn't much in the surroundings that's exerting a force on the system of ball plus Earth, right? So work done. So here's the energy principle. We have change in energy of our system, which is the ball plus the Earth, is equal to the work done by the surroundings. However, what happened to the kinetic energy of our system? Did it change? So the ball starts out at rest and then we release it. So maybe, so think about what really happened here. Think about what's really going on. Did the kinetic energy of the system change? Never mind what you think should have happened. What actually happened? Well, what is kinetic energy? Somebody got a An explanation of what kinetic energy is? Well, what's kinetic energy? Do we have a definition of kinetic energy on the board? That's the approximate expression for kinetic energy when something's moving slowly compared to the speed of light, isn't it? So it's the energy associated with motion, right? That's kinetic energy. The real definition is that it's the total energy of a particle minus its rest energy. So it's whatever extra energy it has due to motion that's on top of just the energy it has by virtue of existing. What happened here, though? Looks like we might have a problem or not. So let's see what you think happened. Okay, so 50%, 51% say the kinetic energy of the system increased. Not too many people said. Well, let's think about the initial and final state. So in the initial state, let's draw pictures. Here's the Earth. Here's the ball. Just after we release it, the instant we release it, speed is 0, right? What's its kinetic energy? 0. So a little bit later, 2 meters later, the ball's fallen. Is its speed 0? No. So V greater than 0, kinetic energy is... Okay, now did the kinetic energy of the Earth change very much? Not really. Because its momentum changed very slightly, but its mass is so big, the change in velocity was infinitesimal. So basically, the kinetic energy of the ball increased, which is exactly what we said the first time, right? I mean, it speeds up. It's moving. It's got. So we kind of have a problem, don't we? It looks like either the energy principle isn't right. So we've got the change in energy of the system is the work done by the surroundings, which you correctly said was 0 because there isn't much in the surroundings that. And what's the change in energy of the system? Well, it's the change in the kinetic energy of the ball plus the change in the kinetic energy of the Earth plus the change in the rest energy of the ball plus the change in the rest energy of the Earth. And since neither of these turned into solid gold or anything like that, we know that their identities didn't change. That was 0. Change in kinetic energy of the Earth was negligible. The change in kinetic energy of the ball was not 0. So it looks like this doesn't work unless we're neglecting another piece of the energy of the system. There's another piece of the energy of this multiparticle system that we haven't included. And that piece is called the potential energy, and it has to do with the energy of interaction between the Earth and the ball, the gravitational interaction between the Earth and the ball. So there is an interaction, and energy is associated with it, because if I pick up an object, even though I'm not changing its kinetic energy, I'm having to exert a force through a distance. I'm essentially stretching the gravitational spring. There's energy being stored in the system of the bottle plus the Earth that we can get back. It's potential energy. We can get it back if we let it go, and then kinetic energy of the system increases. So for a system containing more than one object, there's this potential, there can be a potential energy associated with the interaction between the system. And if we talk about it that way, it makes some sense. So we can rewrite our equation here, change in energy of the system. There's actually another piece. So we have the change in the kinetic energy of the system plus the change in the rest energy of the system, where I'm saying total kinetic energy, total rest energy, plus the change in something that's called potential energy. We use the symbol U for it, and it represents, so this is potential energy, and it's associated with the energy of interaction of a pair of objects. And if our system has lots of pairs of objects, then we have lots of potential energy terms that we'll have to work out. So from our example here, we know that the rest energy didn't change. We know that the kinetic energy of the system actually increased by 1.96 joules, because we calculated the kinetic energy of the ball increasing by 1.96 joules. We know the work done by the surroundings was 0, and that suggests that in this particular case, the potential energy of the system had to decrease, didn't it? It had to decrease by a minus 1.96 joules. Now, to a certain extent, this is just bookkeeping. When we considered only the ball as the system, then the Earth, we said the Earth did work on it, did 1.96 joules of work, and the kinetic energy of the system changed. All the same things still happened, but when we defined the system as both things, there was no work by external objects, but there was something like work by this object that was internal to the system. This 1.96 joules of work was done by forces internal to the system. So it looks like what this is minus the work done by internal forces. And so potential energy, a spring can have potential energy too. It's made up of lots of atoms. So if we stretch the spring, we haven't changed its rest energy. It's at rest, so we haven't changed its kinetic energy. But there's now energy stored in the spring due to the interactions of all those little atoms. And if we release it, we can get that back. So potential energy is actually defined as, the definition is the negative of the work done by forces internal to the system. It turns out to be such a useful way of thinking about energy, because we often want to think about more than one object as the system, that we end up working out expressions for potential energy for a lot of situations that we can then use. So we can think about many situations, we can think about more than one way. Some potential energy is really the only way to do it. So now we actually want to rewrite some of this for a system of more than one particle. So a multiparticle system. And by multiparticle, we might mean a bunch of little particles, but we also might mean big objects. Okay, the energy principle didn't change. It turns out that we have the change of energy of the system is equal to the work done by the surroundings. But now what we have is the energy of the system is equal to the sum of the energies of all the particles inside the system. So the kinetic energy, if we have the Earth and the ball, it's the kinetic energy of the Earth, the kinetic energy of the ball, rest energy of the Earth. So we have the sum of all the K's, and we have the sum of all the MC squareds. And so if we have, we'll write it this way actually. Suppose there's 3 objects in our system, it would be K1 plus K of object 2 plus K of object 3. And then we have M1c squared plus M2c squared plus M3c squared. And then we have another term, plus the potential energy associated with 1 and 2 interacting, and the potential energy associated with 1 and 3 interacting, and the potential energy associated with 2 and 3. So all the pairs of objects have potential energy. You okay with that so far? So one question is, how are we going to calculate this? And that's what we need to work on. So let's think about a situation that's relevant to what you're going to do in lab next week. You've been working with a spacecraft and an Earth and a moon, talking about momentum, but now you're in a position to talk about energy. So you can look at the energy changes of the system as the spacecraft goes around the Earth or goes around the Earth and the moon. And if you consider all three objects as the system, well, you're going to have kinetic energy, but you're also going to have some potential energies. So we're interested in that. So gravitational potential energy, let's see how we're doing. Okay, we can do this. Gravitational potential energy is a very concrete example of potential energy. And so consider two stars. So here's a star, and there's a star. And they're exerting forces on each other, gravitational forces. So if this is the force exerted on star 2 by star 1, how big do I draw the force exerted on this bigger star? Same. Okay, good. Can't fool you. Good job. Not there. And okay, so they start here, and during some period, because this one's smaller, its speed increases more, so it moves farther. So let's say it moves a distance d1. This has a bigger mass, so it doesn't gain as much speed. So during this time, it moves a distance d2. Now, if we took one of them as the system, then we could consider the work done on it by the other one as external work. But if we choose them both as the system, then we need to be able to calculate the change in potential energy of the system in order to figure out the change in kinetic energy of the system. So the change in potential energy of the system, delta U, is just going to be the negative of the work done by these internal forces, where the internal since this whole thing is the system, all these F's are now internal forces, right? And so we want the negative of this F is in the same direction as the displacement d2, so this force, which is internal to the system, does work F times d2. This F is in the same direction as the displacement d1, so we've got, they both do positive work, and so we have, it's the same force times d1 plus d2. And notice that what this says is that it's only the change in the relative position that matters. It's not which one moved how much, because we'd get exactly the same mathematical expression if this one was here and didn't move at all, and that one moved a distance d1 plus d2. So we'd still have an F times d1 plus d2. So it's only the change in R, really. R is the relative position vector. So it's only the change in the relative position that matters, which is convenient. So we can write this as delta U is equal to minus internal work, which is equal to minus, remember we can write this F internal dot delta R, that's the shorthand for minus F internal X delta X, F internal Y delta Y plus F internal Z delta Z. Okay. So if we have let's just do it in one dimension for a minute. So if we have delta U is minus Fx, the x component of the force times delta x, then we can just do a little algebra and write delta U over delta x is minus Fx, and that's going to be true for delta U over y is minus Fy delta y. So, not surprisingly, we could write this as du dx is minus, Fx. So the force is actually the negative gradient of the potential energy. Gradient is a derivative with respect to position, not with respect to time. So if you differentiate, if there's something that's a function of position, you differentiate with respect to position, you're taking the gradient. You're seeing how it changes with position. So our job is actually, so if we can write it as the force is the negative gradient of the potential energy. We have an expression for the gravitational, or more generally, let's write it with respect to R, the magnitude of the separation here. So the gravitational force, the R component of the gravitational force, the component of gravitational force in the direction of R hat, which is going to be a minus G M1 M2 over R. And that's equal to the negative, so minus du dr for some function u. Now we can figure out what the function u is that gives us the gravitational potential energy. So we ought to be able to use this to take an antiderivative, and so we can write u of r equal to something. So all we need to do is take an antiderivative. So let's see how we do this, huh? If du dr, if minus du dr gives us this, what's u as a function of r? So it may help to rewrite this as minus G M1 M2 times r to the minus 1. Oops, sorry, r squared, r to the minus 2. Where did you catch that? You did, all right. Gravitational force, r squared. So is minus ddr of some function. It's clearly going to have a g mm in it, right? So we've got a g m1 m2, and what else? What's the r part? Yeah, 1 over r to the minus 1. And we have to be a little careful. Is that the right sign? Not quite. It's a negative r to the negative 1, isn't it? So basically we're asserting that we're taking the negative derivative of g m1 m2 over r, a minus sign here. So let's differentiate it and see if we actually get the gravitational force, just to be sure. So ddr of minus g m1 m2 over r gives us we're going to get a minus, so what we've really got, we'll rewrite this as minus, there are just a lot of minus signs to keep straight here, so we have a minus gm1 m2 r to the minus 1, and so we're going to have a minus 1 here, so we've got minus g m1 m2 times minus r to the minus 2, and that looks like a minus g m1 m2 over r squared when we get all done, because we've got 3 minus signs, so it's good. So it looks like the gravitational potential energy for two interacting objects is, we can write it as a function of position. So it's a minus g m1 m2 over r, where r is the separation between them. Now notice that there's actually another way we could have, so you don't, this is of course in the textbook, but not necessarily worth writing down, but notice that we should have been able to get it another way, because if two objects, the distance between two objects changes, so it's an R1 and an R2, and we take the gravitational force as an internal force, we could calculate the work done by that internal force. And we should be able to get the same answer, to get a delta U. So we would get delta U is minus the work done by this internal force. Now the problem is that we can't really quite use this. Why not? Is the force constant? The problem is the gravitational force changes as these things get closer together. So what we need to do is basically consider, divide it up into little pieces. We'd take delta R1 and use the force for that part, and then we'd take another piece, delta R2, and we'd have a different gravitational force there, and we'd have delta R3, and we'd have a different gravitational force there. And what are we doing here? Well, we're summing, okay? We're summing again and again, so it's iterative. But what is this in calculus? It's an integral, isn't it? And there's sometimes when we can write an integral we can actually just do with calculus, and sometimes we can't. This is one we can, so it would actually be the minus the integral from R1 to R2 of minus g m1 m2 over r squared dr. And in fact, that would come out to a minus g m1 m2 times a 1 over r2 minus a 1 over r1, which is what we'd get from our equation here. So it works out. Okay. So let's use it. Let's get a number. Got questions about this? We've got our equation. So let's use it to get a number. So here's our problem. There's a rock in outer space, and it's near an asteroid. And it's gravitationally attracted to the asteroid, so it falls toward the asteroid. In fact, it hits the asteroid. And the question is, how fast is it going when it hits? So we have a rock of mass 8 kilograms. and it's initially 100 kilometers away from an asteroid. And the asteroid mass is 2 times 10 to the 16th kilograms. And the asteroid radius is 10 kilometers. And so, in the initial speed of the rock, it's not at rest. So initial speed is 5 meters per second. So how do we calculate this? Well, we're going to use the energy principle, right? So that's overdetermined. So we're going to say E final is E initial plus work done by the surroundings. And there are actually two ways you can do this. You could choose the rock as the system and consider the asteroid part of the surroundings. Or you could choose the rock plus the asteroid as the system, in which case there are no external forces, but there's a potential energy term. So let's do that. And the reason for doing it is we just worked out this lovely function for potential energy. And if we don't use that, then we're going to have to go back to integrating forces. So let's use the system. This is the rock plus the asteroid. And now you're going to have to tell me what to write here for the next step. So, okay, what goes on this side of the equation? Work done by the surroundings is 0. Good. So that's a good reason for choosing both things as the system. Okay, so we have the kinetic energy of the rock, and kinetic energy of the asteroid, and the rest energy of the rock, and the rest energy of the asteroid. And that's potential energy, because there's an interaction between the rock and the asteroid. So we have a gravitational potential energy, and we better put initial subscripts on all this stuff. Anything else? Okay, what goes on the other side? All the same stuff with the subscript final. Okay, so we have K rock final plus K asteroid final plus rest energy of the rock final plus rest energy of the asteroid final plus final gravitational potential energy. Okay, now we look for things that are the same on both sides of the equation. Rest energies for sure. So the rock didn't transmute into something else, so no change. No change. So now we're left with kinetic energies. Does anything else not change very much? Yeah, the kinetic energy, the asteroid doesn't speed up very much. It's a kind of a small rock. So we can also say that the kinetic energy of the asteroid, no change. So now we've actually got a kind of a simpler equation. We have the final kinetic energy of the rock plus the final gravitational potential energy, the initial kinetic energy of the rock, the initial gravitational potential energy. Where's our unknown? Yeah. Well, you think? Is that the unknown? What are we looking for? What do we ask for? Okay, so where's Waldo? Where's the unknown? This one. Okay, in here. Okay. So that's an important step. Figure out which term your unknown's in. So now we better be able to calculate everything else from the given information, right? So let's try it. Okay, how do I calculate the initial kinetic energy of the rock? Okay, so 1/2 mass of the rock, which is 8 kilograms. Initial speed, 5 meters per second squared. Okay. How do I calculate the initial gravitational potential energy of the rock and the asteroid? Okay, so there's a negative sign. That's important. So negative 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Mass of the asteroid, 2 times 10 to the 16th kilograms. Mass of the rock, 8 kilograms. What do I put in for R? Well, it's 100 watts. Kilometers. Do I want kilometers in here? Probably not. What do I want? Meters. So it's 100 times 1,000. So 1 times 10 to the 5th meters. The radius of the asteroid is 10 kilometers, but initially the rock is 100 kilometers away from the asteroid. And remember that in the gravitational force, we're always talking about the center-to-center distances, right? So, yeah. And can we calculate the final? What's the final gravitational potential energy? We better be able to calculate that. Same thing, except what's the only difference is the distance. So we've got a minus 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. We've got 2 times 10 to the 16 kilograms, 8 kilograms. And what do I use for R here? 10 times 10 to the third, right? So it's going to be 1 times 10 to the fourth meters, 10 kilometers. So the rock has just hit the asteroid, right? It started out here, but okay. And now we should be able to calculate. Now notice something here that we could have done. Since the mass of the rock is turning up in every term, we could have actually just divided through by m rock. I didn't do that because I thought it would be interesting to actually get values for these things just to see what they were. So this comes out to, in my opinion, 100 joules. Does anybody else think that's what that comes out to? And this comes out to a negative 107.2 joules. Is that okay? It's negative. It's okay. It's all right. It can be negative. It's fine. And this comes out to negative 1,072 joules. And so when you get all done, you find that this has to come out to 1065 joules, and then you can solve for the final speed, which I believe comes out to something like 16.3 meters per second. So what happened? The kinetic energy increased. Potential energy decreased. Total energy change 0. And it's okay. What is a graph of gravitational potential energy versus displacement going to look like? We'll do more with this next time, but if this is the distance r and this is between the rock and the asteroid, and this is the gravitational potential energy. Well, but there's this negative sign, right? So we've got this 1 over r thing, but it's negative. So when r is really, really, really big, this number is nearly 0, isn't it? And when r is small, so it's going to look something like that. And it's going to be negative, and that's okay. And we'll talk more about that next time. There are examples in the book. I would suggest looking at them. The speed is not always the unknown, so there's a similar example in which you actually need to calculate the mass of something.